Before existence opened its first breath, a fading cosmos drifted into darkness. Its final stars trembled, its last galaxies folded into silence, and the ancient heavens collapsed upon themselves.
Emerging
But from the ruins
the
of that
ashes.
forgotten eternity, a spark awakened. A single flicker of impossible light rising against the void. And in that flicker, a new reality was born. This is the universe that rose from the ashes of the one before it. A universe is expected to begin with violence, with a single, blinding instant where creation erupts from a point smaller than an atom. In that moment, matter, energy, space, time explode outward in a surge so fierce that even now, billions of years later, the echo of that birth still glows across the sky. Or so the story has long been told, yet far beyond the reach of any star. Beyond the dimmest dust suspended in the cosmic night, something quiet lingers. A whisper etched into the fabric of space-time itself. A curvature so slight, it nearly disappears into silence, yet precise enough to defy randomness. A ripple that behaves as though it remembers something our universe should never have known. It hints at the impossible, that our cosmos did not arise from emptiness, but from the fading breath of a universe that came before, like the final heartbeat of a dying world, stretching into the first breath of another. A fire rekindled from ashes no one believed could carry a spark. The cold background radiation. The afterglow of the Big Bang carries patterns to ancient, to ordered, to deliberate. Equations derived from Einstein's relativity curve toward a conclusion both elegant and unsettling. And the oldest photons drifting through the universe seem to bring with them a message older than time's first second. If this is true, then ours is not the first universe to live and die. Not the only. Merely a chapter in a story without a beginning, and without a final page. Tonight, this film follows that whisper. It asks, what came before us? What follows after? And whether the end of a universe is ever truly an end at all? Discovery phase echoes beyond the Big Bang in the first decades of the 20th century. Astronomy stood at the edge of a quiet revolution. The night sky, once believed to be eternal, unchanging, comfortably finite, was about to reveal a truth so vast that it shattered humanity's oldest intuitions about the cosmos. For centuries, the Milky Way had been thought of as the entire universe, a single island of stars surrounded by darkness. Space beyond it, many believed, was merely emptiness. But in 1929, Edwin Hubble, peering through the 100-inch Hooker telescope on Mount Wilson, uncovered a secret the stars had been keeping. The galaxies were drifting away from one another. Not slowly, but with increasing speed. The universe was not fixed. It was expanding. And if it was expanding today, then long ago it must have been smaller, denser, hotter, compressed into something that challenged all imagination. From that revelation emerged the birth of modern cosmology, and with it, the narrative that would dominate science for decades. The universe began in a single, explosive moment. A primordial flash of creation, now known as the Big Bang. This story was compelling, elegant, neat. But science has a way of revealing cracks in even the strongest foundations. By the late 20th century, attention turned toward a subtle field of radiation permeating everything: the cosmic microwave background, or CMB. First detected accidentally in 1965 by Arno Penzias and Robert Wilson, the CMB was hailed as the afterglow of creation, the fossil light left behind when the universe cooled enough for atoms to form. It was thought to be smooth, uniform, a perfect cosmic photograph of the infant universe. But as scientists looked closer, they found that perfection often hides its own mysteries. In 1992, NASA's COBE satellite delivered the first detailed map of the CMB. It revealed faint temperature fluctuations, ripples no larger than 1 part in 100,000. These tiny variations, scientists believed, were the seeds from which galaxies and clusters grew. They were expected, they were predicted, and they fit comfortably within the Big Bang model. Still, some patterns were strange at first. These anomalies were small enough to dismiss. Slight symmetries, unexpected alignments, patches that felt too smooth, Too circular? Too coherent? Were they artifacts? Noise? Glitches in the instruments. The field waited for better data. In 2001, NASA launched the WMAP Observatory, which scanned the sky with unprecedented sensitivity. The results were astonishing not because of what they confirmed, but because of what they refused to explain. The CMB carried scars, subtle ones, but unmistakably real. A cold region larger than theoretical models allowed. A series of circular imprints too organized to arise from random quantum fluctuations. And a strange alignment of low multipole moments, the so-called axis of evil. A name whispered half in jest, half in unease. It was as though the universe's earliest light had been gently pushed, shaped, or influenced by something not accounted for in standard cosmology. But science demands patience. It waits for certainty. In 2013, certainty arrived in the form of the Planck Observatory, a European mission capable of reading the ancient light with a level of precision unimaginable to earlier generations. When Planck produced its full sky map, cosmologists felt a familiar mix of awe and dread. The anomalies were still there, sharper, clearer, more persistent. The universe was not obeying the script among the scientists analyzing. These patterns was a name already. Legendary in physics, Sir Roger Penrose. A figure whose work alongside Stephen Hawking had shaped the modern understanding of black holes, singularities, and the geometry of space-time. Penrose saw something in the Planck data that others had overlooked or perhaps had chosen not to see. He noticed faint circular patterns, nearly perfect rings of slightly elevated temperature, quietly embedded in the CMB map. These circles did not behave like relics of quantum fluctuations. They did not match the expected statistical distribution. They were too defined, too structured, too purposeful. Penrose proposed a daring idea, one that stretched across universes themselves. According to his theory, known as conformal cyclic cosmology, the universe experiences an infinite sequence of eons. Each eon expands for trillions of years, eventually thinning out as black holes consume the last remnants of matter. Over unfathomable timescales, even these black holes evaporate through Hawking radiation, dissipating their mass into faint energy signatures. And then, at the moment when all mass is gone and only radiation remains, something extraordinary happens. The universe resets. A new Big Bang begins. Not from a singularity, but from the exhausted glow of the previous cosmos. Penrose believed the circular hotspots visible in the CMB were the final deaths of supermassive black holes from a universe that existed before ours. Their evaporation, he argued, left behind patterns that survived the transition from one cosmic eon to the next. It was a claim so bold that cosmology itself paused to breathe, if true. These circles were fossils older than time, marks from events that happened not just before stars, galaxies, or atoms, but before our universe had even begun. And yet the data resisted dismissal. The circles were statistically unusual. They were uncomfortably real, and they did not belong to the story of our cosmos as it was currently understood. To grasp the magnitude of this mystery, one must return to the nature of the CMB itself. It is not just light. It is a boundary, a horizon, the edge of what the observable universe can remember. It carries imprints from the first 380,000 years after the Big Bang, a time when the expanding universe cooled enough for photons to travel freely. Everything before that epoch is hidden behind a wall of plasma, a veil through which no electromagnetic signal can pass. Yet here, in that ancient glow, were structures hinting at events that took place before the veil existed. This would require something profound. That information persisted across universes. That the end of one cosmic cycle could imprint its final breath into the beginning of the next. Skeptics argued that these patterns were statistical noise, artifacts of data processing or chance alignments. But the anomalies did not fade. Independent teams saw them. Different instruments measured them. And the circles Penrose identified, though controversial, stacked atop a larger puzzle. Other inconsistencies surfaced. The temperature distribution of the CMB was slightly skewed. The universe appeared to have a preferred direction, a break in isotropy. There were subtle hints of curvature where none should exist. And the largest cold spot in an enormous region, hundreds of millions of light-years wide, defied every model of cosmic inflation, piece by piece. A portrait began to emerge. It was incomplete, fragile, and speculative yet compelling. The earliest light in the universe was whispering about something older, something that did not belong to this cosmos, something that had survived a transition no known physical law permitted. The more scientists studied the data, the more an unsettling realization took root. These anomalies did not behave like remnants of our inflation. They behaved as if they came from a phase of reality predating the Big Bang entirely, and so the impossible question surfaced. What if the universe began not from nothing, but from the death of something else? Penrose's circles were not alone in raising this question. Other researchers found patterns of unusually low variance regions where the CMB was too smooth. A universe emerging from quantum chaos should not have such calm areas unless something before the Big Bang influenced them. Even the curvature inconsistencies hinted at a past geometry, one that survived the transition into our cosmic epoch. Each anomaly alone might have been ignoble. Together, they formed a constellation of doubt. The spark of discovery came when a team compared the expected signatures of evaporating supermassive black holes with the circular hotspots identified in Planck data. The resemblance was haunting. The energy distribution matched predictions. The sizes matched theoretical expectations. And the statistical likelihood of such patterns occurring by chance was unsettlingly low. These signatures looked like the dying breaths of objects that could not have existed in our early universe, because the early universe had no time for such objects to form, evolve, collapse, and evaporate. Yet there they were. If the data was correct, then the final stages of a previous universe, the collapse of its greatest black holes, had left faint fingerprints upon the fabric of our own. For many physicists, this possibility was as thrilling as it was terrifying. It meant cosmology was incomplete, not because it misunderstood our universe, but because it misunderstood the nature of universes themselves, the familiar narrative of cosmic origin, one universe. One beginning, one space-time began to fracture. Perhaps the Big Bang was not a beginning, but a boundary. Perhaps the universe was not born from silence, but from the echo of another's end. Perhaps the cosmos carries memory far older than its own age. As scientists probed deeper, they confronted a chilling truth. The anomalies did not disappear with better data. They sharpened. The temperature rings, the cold spot, the strange alignments, the patterns too perfect to be accidents. Each discovery pressed the same question. Into the heart of cosmology, is our universe truly the first, or merely the latest? The deeper the investigation went, the more the boundary of cosmic time blurred. The Big Bang, a once sacred beginning, now looked increasingly like a doorway. And the universe that stepped through it carried with it faint scars of a world that had already lived and died. Science had not yet proven Penrose right, but neither had it proven him wrong. The ancient light continued to whisper. The equations continued to bend, and the universe, as always, refused to give up all its secrets at once. Scientific shock, contradictions. In SPACITAM, in the history of science, few ideas have ever enjoyed the serenity and confidence of the Big Bang. It stood as a cosmic cornerstone, a singular point from which everything, the galaxies, the atoms, the clocks that govern time, unfolded. It was the cleanest beginning the universe could offer, a boundary so absolute that nothing meaningful could lie beyond it. In this picture, time itself began with the Big Bang. There was no before, because there was no time in which a before could exist. The universe was not only finite in age, it was finite in memory. But science progresses not through comfort, but through disturbance. And the disturbances now arriving from the data, the anomalies etched into the cosmic microwave background, carried implications profound enough to shake cosmology at its root. According to Einstein's relativity, space-time itself emerges from the Big Bang. At t equals 0, the equations describe a singular boundary where density and curvature reach infinite values, rendering the laws of physics incomplete. Nothing, no particle, no energy, no information, should survive or cross such a boundary. If one were to imagine the universe as a long narrative, the Big Bang is chapter 1. There can be no prologue, no earlier edition. The binding of the book is sealed at the spine, yet the patterns revealed by telescopes insisted on an unsettling possibility. Something in our universe seemed to carry echoes of events older than the universe itself. For decades, physicists had embraced the comfort of cosmic inflation, a rapid expansion in the earliest fraction of a second that smoothed out the chaos of the newborn universe. Inflation explained why the cosmos appears so uniform. It explained the distribution of galaxies. It even explained the seeds of structure, a delicate balance of randomness and order frozen into the CMB. What it did not explain were the scars that should not exist. The circular imprints identified in the CMB were too defined to be dismissed as noise. The cold spot, so abnormally large and so improbable, defied statistical expectations. The strange alignment of anisotropies whispered of a cosmic preference for direction, something inflation was never meant to allow. The anomalies did not merely challenged inflation, they challenged the idea that the universe had begun with a true singularity. The scientific shock began with a simple question. How can something leave a trace from a time before time? For a physicist trained in standard cosmology, the question bordered on sacrilege. The Big Bang was not an event within spacetime, it was the event that created spacetime. To speak of a before the Big Bang was to speak of a landscape no mathematics had permission to describe, but science rarely waits for permission. The anomalies continued to sharpen, and their persistence forced cosmologists to confront a contradiction they could not ignore. If the patterns in the CMB were real, then the universe might not have been born from a singular beginning at all. Perhaps the Big Bang was less a creation event and more a transformation. It was in this atmosphere of quiet upheaval that Roger Penrose entered the debate with a theory as bold as it was elegant: conformal cyclic cosmology, or CCC. Penrose proposed that the universe undergoes endless cycles or eons, beginning with a Big Bang and ending in an era where all matter eventually dissolves into pure radiation. Over unimaginable stretches of time, black holes consume galaxies, only to evaporate through Hawking radiation until the last remnants of mass vanish. And in that strange future when nothing remains that can measure time, the universe becomes conformally stretched. The distinction between moments fades. Time loses its meaning, and what appears to us as the cold, empty death of the universe transforms in a new mathematical frame into the hot, dense conditions required for the next Big Bang. In this picture, the universe does not begin at a singular point. It emerges from the final breath of the previous eon. This idea was not merely philosophical. Penrose argued that the circular hotspots in the CMB, now infamously called Hawking points, were the fingerprints of supermassive black holes from the previous universe completing their evaporation. Their final energy release, smeared across the end of one cosmic era, reappears as faint circles in the earliest radiation of the next. Mathematically, the idea was breathtaking. Cosmically, it was unsettling. Emotionally, it was transformative. If Penrose was correct, then our universe was not the first. It was an heir, a descendant, continuation of a storyline older than space-time itself. The contradiction deepened. The Big Bang could no longer be viewed as an absolute boundary. It was a phase change, a transition, bridge connecting eons across unimaginable expanses of entropy and time. The shock reverberated through scientific circles. For many cosmologists, CCC felt almost heretical. The Big Bang was meant to be incontrovertible, a moment beyond which physics dared not speak. Yet here was a Nobel laureate proposing that the universe might be older than its own age, that it carried scars from a predecessor that lived and died in cycles of unimaginable grandeur. Some dismissed Penrose's circles as statistical illusions. Others argued that inflation already accounted for most observations, and the anomalies could be smoothed out with minor adjustments. The debate was fierce, not because the theory lacked elegance, but because it demanded that cosmology rewrite its origin story. If CCC was correct, then the universe was not a singular event. It was a sequence, a long chain of births and deaths, each universe giving rise to the next in an unbroken lineage of cosmic inheritance. The emotional impact of this possibility was profound. For over a century, humans had been told that the universe had a beginning, a unique moment when everything came into existence. The Big Bang was a cosmic genesis. It's a rare and privileged moment where physics and creation intertwined. But now, the data whispered something different. The universe might be infinite in time, yet finite in memory. It might be part of an endless procession of worlds, each one carrying faint echoes of the last. What disturbed scientists the most was not the idea of multiple universes. That concept had existed in various forms for decades. Rather, it was the idea that our universe might remember a previous one. Memory implies continuity. Continuity implies connection. Connection implies that the boundary between universes is permeable in ways physics had long denied. This was the true scientific shock. The laws of physics, once thought pristine and complete, now appeared to be whispering about events they were not meant to record. Relativity had declared the Big Bang to be the beginning of time, yet the oldest light in the cosmos carried imprints of something older. Quantum theory, with its probabilistic haze, did not forbid cycles, nor did thermodynamics. If entropy could be reset in the transition between eons, even general relativity, despite its elegance, was incomplete at the singularity. Perhaps, Penrose argued, the singularity never existed in the first place. Perhaps the universe never truly began from nothing. The shock waves spread through the philosophical heart of cosmology. If the universe had a before, then what determined its fate? Did it ancestors? Did it also have descendants? If the Big Bang was not unique, then neither was our place within it. The skepticism was intense. Many physicists demanded more precise models, more rigorous statistics. Others pointed out that detecting faint circles in the CMB was exceptionally difficult, and interpretations varied across teams. But despite the criticisms, the anomalies remained. They did not vanish under scrutiny. They did not dissolve into noise. They persisted, as though waiting patiently for the next advance in understanding. This persistence created a tension, one not only scientific, but emotional. Cosmology had long relied on the comfort of a clean beginning. It offered simplicity. It offered closure. But now the universe seemed unwilling to provide such comfort. It gestured instead toward a deeper mystery, one in which creation and destruction were intertwined, one in which the universe might be reborn not from emptiness, but from the ashes of worlds long forgotten. It was as if space-time itself were murmuring beneath the equations, hinting that the cosmos is older, stranger, and more layered than any model yet dared to depict. This whisper unsettled physicists, not because it contradicted data, but because it expanded it. The universe was beginning to look less like a singular story and more like a saga in which each chapter ends with dissolution, only to ignite again as a new chapter begins. The shock, then, was not merely scientific. It was existential. The laws of physics, once thought timeless, seemed to shift under the weight of this new interpretation. They appeared to be suggesting that universes themselves could be born, live, and die in cycles beyond human imagination. And somewhere within the faint glow of microwave radiation lie the fingerprints of that deeper history. The contradictions in space-time were no longer anomalies to be dismissed. They had become invitations. Invitations to look beyond the boundary of our cosmic birth and consider the possibility that the universe is not a singular miracle, but one moment in an eternal rhythm of beginnings and endings, a rhythm that continues still. A rhythm that connects us to a universe that came before. A rhythm that will guide the universe yet to come. Deeper investigation. Instruments thein the history of cosmology. Few investigations have reached as deeply into the fabric of reality as the search for anomalies in the cosmic microwave background, the faint afterglow left, right behind by the universe's earliest moments. Scientists had long believed this radiation to be a near-perfect relic, a soft and uniform whisper from the dawn of time. But as instruments improved, as resolution sharpened, and as ambition grew, something unexpected happened. The universe began to reveal patterns it was never meant to contain. The first hints emerged in the early days of satellite cosmology, but the deeper investigations, those that truly exposed the universe's hidden scars, came from a trilogy of instruments: the Planck satellite, the Keck array, and the South Pole telescope. Each instrument carried a unique eye, a different sensitivity, and a different method of reading the cosmic background. Together, they formed a network of vision capable of probing the oldest light with a precision that would have been unimaginable only decades before. The results changed everything. Planck was the first to deliver the shock with extraordinary clarity. Launched by the European Space Agency in 2009, it mapped the entire sky in microwave wavelengths, producing the highest resolution image of the CMB ever created. It did not simply confirm earlier findings, it sharpened them, exposing delicate patterns hidden beneath noise, refining the contours of cold spots and temperature gradients, and revealing with brutal honesty the structures that defied explanation. Among these structures were temperature rings, circular regions with shockingly uniform profiles. In the standard model of cosmology, such rings should not exist. Quantum fluctuations in the early universe are messy, chaotic, and statistically random. But these rings were smooth, too perfect to have emerged from chance. They resembled the theoretical signatures predicted by Roger Penrose in his conformal cyclic cosmology, Hawking points. The final energetic death cries of supermassive black holes from a universe that ended before ours began. The idea was extraordinary. According to CCC, when black holes evaporate through Hawking radiation, they release their final energies in bursts that, when viewed through conformal geometry, become circular imprints in the next universe's cosmic background. These imprints should appear as faint, warm circles, exactly the kind of anomalies Planck was detecting. The shock was not merely scientific. It was emotional. The universe had always been viewed as a singular entity, a lone stage upon which the drama of existence unfolded. But now, the data suggested a lineage of continuity across cosmic cycles, a universe born not from silence, but from inheritance. Planck's revelations were only the beginning. To understand the anomalies at a deeper level, cosmologists turned to the background imaging of cosmic extragalactic polarization and Keck array experiments. Stationed at the South Pole, where the air is thin, dry, and stable, perfect for observing faint cosmic signals. These instruments did not look for temperature maps, but for polarization patterns, the orientation of the light waves themselves. Polarization contains subtle fingerprints of the universe's inflationary era, including the elusive B-mode patterns that could confirm gravitational waves from the dawn of time. But as Bike examined the sky with increasing precision, their data began to reveal features that were inconsistent with a clean inflationary signal. Instead of finding the expected random distribution of polarization, they found alignment patterns eerily consistent with the directional anomalies seen by Planck. These alignments deepened the mystery, suggesting that the universe possessed a preferred orientation, a kind of cosmic fingerprint that inflation should have erased. Inflation, after all, is supposed to stretch the universe so dramatically that any pre-existing structure becomes utterly unrecognizable. It turns chaos into uniformity. It smooths out curvature, eliminates directionality, and ensures that the universe looks the same in all directions. But the data refused this narrative. The polarization patterns hinted at a universe that had inherited structure subtle but undeniable from something that came before inflation. The implications were tremendous. If inflation had not erased the evidence of a previous cosmic phase, then inflation itself was incomplete, or perhaps not the entire story. The investigation deepened further with the South Pole Telescope, SPT, a powerful instrument designed to detect variations in the CMB at small angular scales. Where Planck offered broad, sweeping detail, the SPT delivered fine-grained resolution, like shifting from a telescope to a microscope. JWST examined the CMB cold spot, an enormous region of the sky anomalously cooler than the surrounding space. While some argued it was simply a statistical fluke, others suspected something more dramatic, a remnant of a cosmic collision, an imprint of a bubble universe brushing against our own, or perhaps a final echo of energy from a collapsing region of a prior eon. But as SPT refined the cold spot's profile, a strange truth emerged. The cold spot did not behave like a random temperature depression. Its center was smoother than models predicted. Its edges were sharper, and its shape aligned too cleanly with other large-scale anomalies among them, the infamous axis of evil, a directional alignment of temperature multipoles that had haunted cosmologists since the early 2000s. These alignments should not exist. They violate the principle of isotropia, the assumption that the universe has no preferred direction. Inflation should have obliterated any such pattern. And yet the patterns persisted, whispering of a deeper structure beneath the universe's apparent symmetry. Together, these observations painted a startling picture. The anomalies were correlated. They reinforced one another. They were not accidents. It was as if the universe were layered or cosmic backgrounds sitting atop a hidden substrate, the remnants of a cosmic phase predating everything we know. To understand these findings, one must return to the essence of inflation. According to standard cosmology, inflation occurred in the first 10 to 32 seconds after the Big Bang, expanding the universe exponentially and flattening its curvature. This process should erase any memory of prior conditions with ruthless efficiency, yet the anomalies suggested that memory had survived the unnatural smoothness of temperature rings, the directional coherence of polarization patterns, the gravitational signatures hinting at curvature from another epoch, the strength and persistence of the axis of evil, the statistical improbability of the cold spot. Each anomaly could perhaps be explained alone, but together, they formed a network of contradictions too organized to ignore. Scientists began to consider the unthinkable. Inflation might not be the entire story, or it might be operating atop a deeper structure inherited across cosmic cycles. The deeper investigation now shifted toward mathematics, the silent architecture beneath cosmology. If the universe bore signatures of a prior existence, then the geometry connecting one universe to the next had to be extraordinary. Penrose's conformal transformations offered one possibility. In CCC, the infinite expansion of a universe thins out matter until only radiation remains. In that final state, where no massive particles exist to measure time, the geometry of the universe becomes scale invariant, allowing its end to map smoothly onto the beginning of a new universe. Mathematicians refined these ideas. They examined how the boundaries of one space-time stretched infinitely thin could fade into the geometry of the next. They studied conformal diagrams, causal structures, and the behavior of curvature under scale transformations. The equations were complex, abstract, and philosophically challenging. Yet they offered something no alternative model had provided: a mechanism by which information could survive cosmic death. The notion that black hole evaporation could leave behind imprints was controversial, but it offered a tantalizing link. If supermassive black holes from the previous universe released their final energies in a slow crescendo before vanishing, those energies might imprint faint, circular anomalies into the geometry of the next universe's early radiation. The data matched these predictions with unnerving precision. As the investigations deepened, cosmologists found themselves confronted with a new question, one that grew louder with every new observation. If the death of one universe gives birth to the next, then what does that make our universe? A continuation? A descendant? A memory? The philosophical implications were immense. The universe was no longer a standalone entity with a singular beginning. It was a chapter in a sequence of eons, each carrying echoes of the last. Time became cyclical. Creation became renewal. The Big Bang transformed from a boundary into a bridge. Scientists felt the weight of this idea. For decades, cosmology had enjoyed a sense of stability, grounded in equations that seemed to describe everything. But now, the deeper investigations revealed cracks, not in the data, but in the assumptions beneath them. If anomalies survived inflation, then inflation was incomplete. If patterns endured across cycles, then the universe remembered. If black holes left signatures in the next cosmos, then the boundary between universes was permeable. These possibilities unsettled even the most seasoned physicists. The instruments had seen too much. Planck revealed rings that should not exist. B, ICEP, and Keck revealed alignments that defied randomness. The South Pole telescope sharpened the cold spot into a puzzle too profound to dismiss. One by one, the universe surrendered its secrets not with clarity, but with contradiction. The deeper the investigation went, the more the evidence suggested continuity, an unbroken thread weaving together the end of one cosmos and the beginning of another, a tapestry stretching across eons, stitched together by the strange geometry of conformal boundaries. The universe, it seemed, did not erupt from nothing. It flowed from the ashes of what came before, and every new instrument, every new map, every new polarization pattern brought cosmologists closer to accepting a truth more ancient tanned, more radical than the Big Bang itself. The universe carries memory. Memory older than time. Memory inherited across cosmic death and rebirth. Whether the scientific world was ready to accept such a revelation did not matter. The evidence was there. The data was clear. The universe had spoken. It was time to listen. Escalation. When the mystery dawned upon us, the deeper scientists ventured into the anomalies of the cosmic microwave background. The more the universe seemed to resist the comfort of singular explanations. What began as a handful of curious deviation circles that were too smooth, alignments that were too precise, cold regions that were too vast, soon formed a tapestry of contradictions woven across the sky. These patterns did not dissolve with better data. They sharpened. They multiplied. They deepened into something that felt less like noise and more like a quiet confession from the cosmos itself. To understand this escalation, one must step beyond the familiar timeline of cosmic evolution and into the distant future of futures so remote, so stretched across trillions upon trillions of years that even imagination strains under its scale. Modern cosmology predicts that the universe will continue to expand for as long as physics allows. Galaxies will drift apart until they vanish beyond one another's horizons. Stars will exhaust their fuel and fade into cold embers. Matter itself will become thin, scattered, and quiet. In this far future, only black holes will remain. Titanic structures. Collapsed remnants of collapsed stars and merged galaxies, holding within them the last significant reservoirs of mass, and then even they will not last. Stephen Hawking's remarkable insight, now a cornerstone of theoretical physics, revealed that black holes are not eternal. Through a slow evaporation process driven by quantum effects near their event horizons, they radiate energy into space. Over timescales so vast they defy expression, black holes gradually lose mass. A stellar black hole may evaporate over 1,067 years. A supermassive black hole like those at the centers of galaxies may require 10,100 years or more. Yet eventually, inevitably, even the greatest black holes will evaporate completely, leaving behind a final burst of energy as their last imprint upon existence. In the standard model of cosmology, this is where the universe's story ends. After the era of black holes, the universe enters its so-called heat death, a silent, cold expanse where entropy can no longer increase, where no structures remain, and where time loses all meaning because nothing is left to change. It is a lonely ending, a slow dimming of the cosmic stage, but in Roger Penrose's conformal cyclic cosmology, this ending is not an ending at all. In CCC, the death of all matter, its reduction to pure radiation removes the last obstacle preventing a radical mathematical transformation. When the universe becomes completely massless, the geometry of space-time shifts. Without mass, there is no scale. Without scale, distance loses its conventional meaning. The universe becomes conformally stretched. allowing the infinite future of one cosmic era to connect seamlessly with the Big Bang of the next. What appears to us as the end of time becomes, in another mathematical frame, the beginning of a new universe. It is in this transition that the signatures of evaporating black holes survive. Their final releases of energy become faint circular imprints, Hawking points visible in the newborn universe's cosmic background. In this way, black holes, the engines of annihilation, become the final storytellers of the cosmos, carrying whispers of one universe into another. This idea alone was dramatic enough. It suggested that the universe might be cyclic, that each cosmic era inherits the last breath of the one preceding it. Yet the true escalation arrived when scientists realized that not one, but many independent anomalies bore striking consistency with this model. The temperature rings were the first, but they were soon joined by anomalies in polarization, strange alignments in the CMB multipoles, and oddly persistent gravitational signatures. Each anomaly alone might be dismissed as coincidence. Together, they formed a structure, subtle but undeniable. The universe was not merely whispering. It was repeating itself. For cosmologists trained in the Standard Model, this was deeply unsettling. The Big Bang was supposed to be the absolute beginning. Relativity insisted on a boundary at t=0 beyond which physics could not speak. Inflation promised to erase all traces of prior structure. Yet the anomalies suggested continuity, inheritance, and memory. The scientific shock of earlier chapters now condensed into something heavier, something more profound. If these signatures were real and their persistence across datasets implied they were, then our universe was not a singular creation. It was one link in a chain. One cycle in a sequence of universes stretching backward beyond comprehension. In this new vision, the cosmos did not explode into being from nothing. It grew from the death of a previous universe. And our universe, too, would someday give birth to the next. This escalation did not merely reshape equations. It reshaped existence. Imagine the scale of this cycle. A universe expands for trillions of years. Stars ignite and die. Galaxies collide and merge. Civilizations, if they arise, live and vanish long before the final black holes evaporate. And then, in a moment of incomprehensible quiet, the universe becomes thin enough, empty enough, weightless enough for geometry itself to transform. The Big Bang of the next universe is not a separate event. It is the transformed, it's the future of the previous one. The circular anomalies seen in the CMB are not random. They are fossils, echoes, memories of black holes that lived and died before our universe began. Scientists began to layer the anomalies on top of one another. The cold spots' improbable geometry, the polarization alignments, the temperature rings, the axis of evil's directional preference. They found a haunting coherence. Not a perfect picture, not a complete map, but a network of evidence pointing toward continuity between universes. The deeper they looked, the more the mystery deepened. If universes arose in cycles, then our universe was neither unique nor privileged. It was not the first. It would not be the last. It was one iteration in a vast, perhaps infinite procession of cosmic eras, each shaped by the ashes of the last, each giving rise to the next. This realization carried heavy philosophical weight. Humanity has often imagined itself positioned near the center of cosmic significance, first geographically, then biologically, then temporally. But each advancement in science has pushed humanity farther from the center. First, Copernicus displaced Earth from the center of the cosmos. Then Darwin displaced humans from the center of creation. Now, cosmology threatened to displace the entire universe from uniqueness. Instead of the universe, there might be a universe. Instead of a singular beginning, endless beginnings. Instead of finality, repetition. This was not merely scientific escalation. It was emotional escalation. It required confronting a universe more immense than any previous model had allowed. A universe without a true beginning. A universe without a final end. a universe in which death and birth were indistinguishable in the grand scope of cosmic time. But there was something even more unsettling. If patterns survived the death of a universe, then so might deeper structures, laws, symmetries, even constants. Perhaps each universe did not simply follow the last. Perhaps it inherited its tendencies, its geometry, its cosmic fingerprints. The universe's apparent fine-tuning, long a mystery, could be the result of inheritance, not accident. Scientists confronted a terrifying implication. The universe was not simply expanding. It was repeating, perhaps endlessly. And if that was true, then the nature of time itself was at stake. Time would not be a straight line from beginning to end. It would be a loop stretched across eons, a spiral across infinities, a rhythm in which each note was a universe, each chord a cycle, each era a breath in the lungs of eternity. The anomalies in the CMB were no longer minor curiosities. They were evidence of this rhythm. Their alignment was too consistent, their persistence too stubborn, their structure too deliberate to dismiss. The universe was not random. It carried memory as models grew more sophisticated. Mathematicians refined how one universe's final geometry could fade into the opening geometry of the next. They examined how conformal boundaries could compress infinity into a singular moment. They explored how massless fields could glide across the boundary between eons, painting faint patterns upon the newborn cosmos again and again. The numbers returned to the same conclusion: continuity. The death of one universe transitioned smoothly into the birth of another. This idea did not replace the Big Bang. It reframed it. The Big Bang was not the beginning. It was the rebirth. Scientists now found themselves in unfamiliar territory, a universe whose deepest mysteries were not hidden in its earliest moments, but in its final ones. The end of a universe became the key to understanding the beginning of ours. And so the mystery deepened, not because the universe grew darker, but because it grew larger, more ancient, more cyclic, more alive. What humans once called the universe became, in this new vision, a single heartbeat in a cosmic organism, a single wave in an endless ocean, a single breath in the lungs of a boundless, ageless multiverse of cycles. And this revelation, as unsettling as it was profound, pushed cosmology into a new era, one in which the universe's past and future were not divided by a singular boundary, but woven together through the geometry of time itself. Scientists now stood before a question, both beautiful and terrifying. If our universe inherited the echoes of a previous cosmos, what echoes will we leave for the next? Theories and speculations, the physics of a universe born after an endymion, the search for the universe's deepest origins. Science often returns to familiar boundaries, mathematical walls, where known physics shatters into unknowable infinities. The Big Bang is one such boundary, a moment so dense, so compressed, so absolute, that the equations describing it refuse to speak further. It is a curtain drawn across time, a veil hiding whatever came before. For decades, this was where cosmology stopped. Behind the curtain was silence. But the anomalies in the cosmic microwave background, those strange circles, alignments, and gravitational whispers suggest the curtain may not be truly opaque. Instead, it may be thin, permeable, a membrane between two eras, rather than the edge of existence. And so, physicists began to explore the possibility that the universe did not begin after nothingness, but after something else. What followed was a blossom of theories, some rooted in established mathematics, others emerging from the most daring edges of quantum gravity. Each theory attempted to answer a single question: how can a universe begin after an end? The answers were as varied as they were profound. The first and most influential was conformal cyclic cosmology. Roger Penrose's radical and elegant model. At its heart lies an idea both simple and astonishing. If mass fades away at the end of time, the universe becomes scale-free. Without mass, distances lose their meaning. Without scale, infinite time can be mapped onto a single moment. A universe stretched thin by trillions of years of expansion can be transformed mathematically into a dense, hot beginning. The physics of CCC rests on conformal geometry, a branch of mathematics that preserves angles but not distances. In such a geometry, the infinite future of one universe can connect smoothly with the Big Bang of the next. The boundary between eons becomes a conformal bridge. As the universe expands and ages, mass slowly disappears. Black holes evaporate. Particles decay. Even proton decay, a hypothetical process with a lifetime longer than the entire current age of the universe becomes inevitable in the distant future. Eventually, only photons remain, massless and scaleless. In that future, clocks no longer tick. The notion of time dissolves. The entire cosmic stage becomes conformally equivalent to the hot, dense conditions at the beginning of a new universe. This is the heart of Penrose's vision. The end of one universe mathematically transforms into the birth of the next. In this picture, black holes play a pivotal role. As they evaporate through Hawking radiation, they release their final energies in bursts that propagate across the conformal boundary into the next cosmos. These bursts form Hawking points, the circular hotspots seen in the CMB that sparked this entire investigation. According to CCC, the black holes of the previous universe are the storytellers of the next. Their dying breaths become the earliest whispers in our cosmic background. This model does not merely allow a universe to be born after an end. It requires it. But CCC is not the only path toward. It's a cyclic universe. Another framework emerged from the efforts to unify quantum mechanics with general distributivity. Loop quantum cosmology. The cosmological extension of loop quantum gravity. In this theory, space-time is not a smooth, continuous fabric, but a discrete network woven from tiny loops of quantum geometry. At extremely small scales, these loops resist compression, preventing the formation of a traditional singularity in LQC. The universe does not crash into an infinite point at the Big Bang. Instead, it undergoes a quantum bounce. The universe contracts. Density increases. Curvature rises. But as it approaches Planck scale conditions, a repulsive quantum pressure emerges, halting the collapse. Instead of a singularity, the universe rebounds. It expands again. In this view, the Big Bang is not a beginning, it is a bounce. A moment of transition between a collapsing universe and an expanding one, where CCC connects cycles through conformal geometry. LQC connects them through quantum geometry. Both bypass the impossibility of a singularity by replacing it with a transition. Both describe a universe born from a previous one. But where CCC envisions a universe stretched into weightlessness before the next begins, LQC envisions a universe crushed into a quantum heartbeat that rebounds outward. In this model, remnants of the pre-bounce universe could leave imprints in the earliest radiation of the post-bounce universe, possibly explaining the persistent anomalies that inflation alone cannot erase. The bounce is not gentle. It is violent, yet it is continuous. It preserves information, structure, and geometry in ways classical cosmology never envisioned, and it suggests a universe older than its own beginning. A third possibility arises from the strange landscape of quantum fields. False vacuum decay. In this scenario, the universe does not end by fading into emptiness, nor by collapsing into density, but by transitioning between states of energy. According to quantum field theory, space itself is filled with energy, the vacuum energy. Our universe may be trapped in a metastable or false vacuum, not the lowest possible energy state, but a temporary one. If the vacuum were to decay through quantum tunneling or other fluctuations, it could trigger the birth of a new universe within the old. A bubble of true vacuum would form, expanding at nearly the speed of light. Inside this bubble, the laws of physics could differ. The constants could change. The geometry could shift. The bubble would grow, forming a new universe with its own space-time, its own arrow of time, its own evolution. The old universe might continue outside, or it might collapse. But inside the bubble, a new cosmic story would begin. Vacuum decay offers a universe within a universe, a cosmic nesting of realities. It does not require a previous universe to die, only for a new one to nucleate. In this sense, the universe may be eternally generative, producing pockets of new space-time from quantum instability. The philosophical implication is stunning. A universe does not need an end to create a beginning. Creation is embedded within destruction. It's written into the vacuum itself. A fourth possibility expands into even grander territory, the multiverse of cosmic inflation. In eternal inflation, universe constantly spawns new regions, bubble universes each with its own Big Bang. Inflation ends in some regions, giving rise to universes like ours, but continues in others, endlessly generating new cosmic domains. In this view, our universe is one bubble among countless others. Each bubble may differ in fundamental constants, dimensions, or physical laws. Some universes may resemble ours. Others may be unrecognizably alien. Each bubble's end, whether through decay, cooling, or collapse, may seed further expansion in a parent inflationary field. The multiverse becomes a cosmic ocean, its waves rising and falling in perpetual creation. In this model, universes are not sequential, but parallel. They arise simultaneously, not in a chain, but in a foam. Yet the anomalies in our CMB may hint at collisions between these bubbles, events in which two universes, drifting through the inflating medium, brushed against one another, leaving circular imprints in their cosmic backgrounds. Here, the end is not a boundary. It is an interface. The universe becomes porous, its edges soft, its beginnings intertwined with the births of others. Fifth family of theories comes from the thermodynamic heart of cosmology, models in which entropy resets at cosmic death. According to the second law of thermodynamics, entropy, the measure of disorder, always increases. A universe that expands endlessly becomes increasingly disordered. Yet many physicists have long struggled with the fine-tuning present at the Big Bang. The universe began in an extraordinarily low entropy state. How did order emerge from disorder? One answer is that entropy resets, that new universes begin in states of exceptional order because the collapse or evaporation of the previous universe removes entropy. In some models, the universe cycles through phases separated by entropic cleansing events, collapses, bounces, phase transitions, or conformal stretches. In others, entropy is diluted across infinite expansion. It's preparing the conditions for a new beginning. In these theories, the death of a universe is a purification, a renewal, a resetting of cosmic possibility. The images they evoke are almost mythic. A universe burns out, only for its ashes to cool into the perfect seed of a new cosmic bloom. These theories loop quantum cosmology, false vacuum decay, inflationary multiverse, thermodynamic cycles, do not compete so much as enrich one another. They offer different visions of how universes may arise from endings. They explore different mechanisms through which information could bridge cosmic eras. They paint different pictures of creation, each grounded in mathematics, yet each extending beyond the boundaries of known physics towards something deeper. Together, they form a chorus of speculation speaking to a profound idea. The universe does not begin. It continues. This idea carries profound philosophical weight. Does time have a beginning, or is it a circle? Are universes children of their predecessors? If so, do they inherit laws, structures, or tendencies? Does creation require destruction? Is the universe itself a living sequence breathing in expansion? Breathing out in collapse, its heartbeat measured in eons rather than moments. Perhaps the biggest question is the simplest. If our universe was born from the end of another, will the next be born from the end of ours? The theories differ in detail, but they converge on one truth. What humans once called the beginning may only be a transition. What humans once called the end may be the threshold of renewal. In these models, the cosmos is not a singular miracle. It is a lineage, a dynasty, an eternal rhythm of light emerging from darkness, order emerging from collapse, beginnings blooming from endings. The universe becomes not a solitary creation, but one voice in an ancient choir-rich universe, singing its verse, passing its final note into the opening chord of the next. Scientific tools and ongoing testing, searching for cosmic enhanced ESTR wire, cross the vast timeline of human curiosity. There's never been an era quite like this one. For the first time, humanity possesses instruments capable of reaching not merely across space, but across time itself. Tools capable of reading the earliest light, the faintest gravitational ripples, and the most delicate quantum traces left behind by the universe's birth. And perhaps, if the recent anomalies are to be believed, traces left behind by the death of a universe that came before. To search for cosmic ancestry is to attempt something at the very edge of imagination. It requires telescopes that can see the first stars ignite, detectors that can hear the universe tremble, and particle colliders that can recreate conditions only moments after the Big Bang or the end of a cosmic cycle. It is an endeavor driven by a single question. If another universe existed before ours, can its fingerprints still be seen? The search begins not with speculation, but with instruments already looking deep into the past. The James Webb Space Telescope stands as humanity's newest eye upon the cosmos, orbiting beyond the moon's shadow, cooled to frigid silence. JWST peers back across more than 13 billion years of cosmic history. Its infrared vision reveals the first galaxies, forming only a few 100 million years after the universe began. These structures may contain clues to whether the early universe behaved as expected, or whether it carried anomalies inherited from a prior cosmic era. JWST was designed to study the first light, but its findings already hint at something unusual. Galaxies appearing too early, too massive, too complex for standard cosmology. Structures forming faster than models predicted. These are not yet proofs of cosmic ancestry, but they are suggestions, subtle deviations that may reflect an inheritance. Written into spacetime long before stars and matter assembled, if the universe carries memory, JWST may be the first instrument to glimpse its echoes in the formation of cosmic structure, where JWST observes ancient starlight. Another instrument studies something even older, the faint polarization patterns etched into the cosmic microwave background. On a high plateau in the Chilean Andes, where the air is thin and the sky is clear, the Simons Observatory resizes a collection of telescopes designed to read the CMB with unprecedented sensitivity. It seeks the fingerprints of inflation. It's the tiny curls and twists in polarization known as B-modes. But it also seeks something stranger. If the CMB anomalies Hawking points, circular patterns, the axis of evil or real, then the Simons Observatory is ideally positioned to verify them. Its ability to map polarization across a wide range of scales offers a powerful test. Are the anomalies reproducible, or are they artifacts of earlier instruments? A reproducible anomaly is not an anomaly. It is evidence, as the observatory refines its maps. Scientists await whether it will confirm the faint rings predicted by conformal cyclic cosmology. Polarization is harder to misinterpret than temperature, making it a decisive battlefield in the search for proof, and preparing to join it is another. Instrument 1 even more ambitious. The upcoming CMB's 4 project is designed to test inflation itself. It will be the most sensitive survey of cosmic microwave radiation ever undertaken. Spread across both the South Pole and the Chilean desert, CMB's 4 will scan the sky with detectors numbering in the hundreds of thousands, seeking the primordial fingerprints of gravitational waves ripples that could have been produced during inflation in the universe's first instant. But CMB's 4 serves another purpose. It will test whether the faint anomalies observed by Planck are real features of the cosmos, or remnants of noise and statistical chance. If CMB's 4 finds the same rings, the same alignments, the same temperature, gradients too uniform to be random, then the weight of evidence will shift dramatically. The universe will no longer appear as a blank canvas after the Big Bang, but as a canvas lightly marked by memories from an earlier age. Such confirmation would be nothing short of revolutionary. While the cosmic microwave background offers a portal to the earliest light, Particle physics offers a portal to the earliest conditions. The Large Hadron Collider, buried beneath the border of France and Switzerland, smashes protons together at energies approaching those of the universe's first microseconds. Its aim is not merely to discover particles, but to probe the stability of the vacuum itself. If the vacuum is metastabile, false vacuum, perched above a lower energy state, then the universe may be sitting atop a cosmic precipice. In such a scenario, vacuum decay could trigger the birth of a new universe within our own. Just as some theories of cosmic ancestry propose, physicists study the Higgs field-quark interactions and quantum fluctuations to determine how close our universe lies to that boundary. The answer could illuminate whether the universe is destined to end in decay, collapse, or infinite expansion, and whether its end could spark the beginning of a new cosmic cycle. The LHC also tests whether particles or symmetries predicted in cyclic or bouncing cosmologies exist. Supersymmetric particles, econs, and other exotic entities might serve as messengers from the boundary between universes. Their detection or absence holds clues about how the universe transitions from one era to another, yet perhaps the most haunting tool in the search for cosmic ancestry is not a telescope or a collider, but an eye-rand ear tuned to the trembling of space-time itself. The LIGO, Virgo, and Cagra observatories measure gravitational waves, ripples in space-time produced by massive objects in motion. Their detectors are so sensitive they can feel the passing of waves smaller than a proton's width. These observatories have already revealed collisions of black holes and neutron stars, events unfolding billions of light-years away. But they also search for something far older: primordial gravitational waves, vibrations produced before the cosmic microwave background itself, possibly during inflation or a pre-Big Bang phase. If the universe existed before ours, then the transition between eons through a conformal bridge, or quantum transition, could have released gravitational waves of immense energy. These waves might still echo through space-time today, faint but detectable. Such a detection would be nothing less than a message from before time. The search is ongoing, and the sensitivity of gravitational wave observatories continues to increase. Future upgrades may allow them to hear waves far older than any light in existence. The questions scientists now ask are remarkably specific and remarkably bold. Are the CMB circular anomalies reproducible? If so, they form a pattern that no inflationary scenario can easily explain. Can we detect signatures consistent with black hole evaporation from a prior universe? These would appear as localized temperature elevations, Hawking points, or spectral deviations in the CMB. Can space-time geometry itself confirm a cyclic cosmology? Mathematicians model how conformal stretching or quantum bounces reshape curvature. Observational cosmologists test whether the universe's large-scale geometry hints at such transitions. Across disciplines: astronomy, particle physics, quantum gravity, scientists gather data from every direction, searching for coherence in theories that once seemed too speculative to test. The effort is not merely scientific. It is archaeological. Humanity is digging for fossils buried in the oldest fabric of existence, fossils that may have survived not just billions of years, but an entire cosmic death and rebirth. And while present-day tools are powerful, the next generation will be transformative. The future of cosmic ancestry. Research lies in instruments even more sensitive than those of today: space-based gravitational observatories, such as the proposed LISA laser interferometer space antenna, will drift millions of kilometers apart in orbit, able to detect low-frequency gravitational waves that ground-based facilities cannot. These waves may carry signatures of cosmic cycles, domain transitions, or pre-inflationary phenomena. Next-generation CMB missions, including dedicated satellites with noise levels far lower than Planck, may reveal polarization, patterns so detailed that the faint scars of prior universes become unmistakable. High-altitude balloon observatories, cooled cryogenically and launched above 99% of Earth's atmosphere, may deliver clarity unimaginable today. Even particle physics may undergo a renaissance, with future colliders designed to probe energies far beyond the LHC, capable of exploring the vacuum stability, a landscape that determines the fate of universes in every domain. Humanity pushes toward the same goal, to determine whether the universe we inhabit is one chapter in an ancient cosmic lineage. What drives this pursuit is not merely the anomalies themselves, but the possibility they represent, a chance to uncover continuity across cosmic cycles, a chance to peer through the veil of the Big Bang, a chance to hear the faint echoes of universes long gone. It is a profoundly human endeavor. To seek ancestry is to seek identity. To uncover origins is to understand destiny. If the universe carries memory, then human curiosity becomes the instrument that brings that memory to light. Cosmologists, physicists, mathematicians, and engineers now work side by side to decode these ancient signals. They build machines that stare into darkness. They refine equations that bend space-time into new shapes. They listen to vibrations that ripple across the cosmos, like faint music from a forgotten age. And as each new dataset arrives, as each new instrument sharpens its gaze or its hearing, humanity edges closer to an answer that has eluded it since the dawn of thought. Did another universe exist before ours? And if so, what story did it leave behind? Across laboratories, mountaintops, deserts, and orbit, the search continues. Not for stars, not for galaxies, but for memory, for the fingerprints of a cosmos that died long before ours began, philosophical. Reflection, emotional, close, when the end is never the end, in the quiet stretches of the night sky, where galaxies drift like lanterns carried by an invisible tide. The universe reveals a truth older than any equation. Everything that lives must eventually fade. Stars burn through their fuel and collapse. Galaxies collide and reshape themselves into new spirals of light. Planets crack, cool, and disappear. Even atoms decay. Nothing remains untouched by time. Yet in these endings, something remarkable occurs. A star's death births heavier elements, scattering seeds of worlds yet to form. Galaxies merging tear themselves apart, only to weave new structures from the remnants. What seems like destruction is often the quiet beginning of change. Perhaps the universe itself follows this ancient rhythm. Perhaps it too dies only to become something new. This documentary has traced the faint whispers of something extraordinary patterns in the cosmic microwave background that suggest our universe did not emerge from nothingness, but from the final breath of a universe long vanished. If this is true, then the story of creation is not a single event, but an endless cycle, one universe ending, another awakening, each carrying fragments of cosmic memory across the threshold. It is a humbling thought, yet deeply human. For humanity has always lived between stories, one ending, one beginning, and now. The universe itself may be telling such a story, long before telescopes or mathematics. Humans looked to the stars and imagined themselves central to creation. The heavens revolved around Earth. Earth was the centerpiece of existence. But slowly, science revealed a widening truth. Earth orbits the sun. The sun orbits the center of a galaxy. The galaxy drifts through a universe unimaginably large. And now, even that universe may be only a single frame in a film without end. If universes succeed one another endlessly, then our cosmic home is not the grand total of reality, is a chapter, a single cycle within an infinite sequence. This realization does not diminish humanity. It expands the horizon of what humanity may someday understand. For if the universe carries memory of faint echoes of a previous cosmos, still ripple through our own, then existence is connected in ways deeper than time, space, or physics traditionally allow. It means the fabric of reality is not a blank canvas, but a palimpsest, a layered manuscript written and rewritten with every cosmic cycle. Beneath the ink of our universe lies the faded script of another, and beneath that, perhaps countless others. This is the poetic paradox that haunts modern cosmology. If our universe began after another ended, then somewhere in its deep architecture, the memory of that earlier cosmos still echoes. Not memory as humans know it, no images, no voices, no stories, but the memory of structure, the memory of symmetry, the memory of energy patterns burned into space-time at the moment of transition. These echoes appear as circular anomalies, improbable alignments, gravitational whispers, too subtle for the naked eye, yet too persistent to ignore. They linger quietly at the universe's edges, like faint footprints dissolving into cosmic sand, and if they are real, then humanity stands at the threshold of something extraordinary. The ability to glimpse beyond the boundary of the Big Bang, to look not just backward in time, but backward across universes. This possibility redefines existence itself. For generations, humanity has asked where everything came from, why the universe exists, why the laws of physics are precisely tuned to allow galaxies, stars, life. In a single universe model, such questions drift toward paradox. Why these constants? Why this beginning? Why this improbable order? But in a cyclic universe, meaning emerges through continuity. Each universe inherits tendencies, conditions, and patterns from its predecessor. The fine-tuning puzzle becomes an evolutionary one. The universe's structure becomes the result of cosmic ancestry, not coincidence. In this view, destruction is not an end. It is a passage. Creation is not a singular moment. It is a rhythm. And the Big Bang is not a boundary. It is a doorway. To think this way is to loosen the grip of human-centered time. Lives measured in decades cannot easily grasp cycles measured in trillions of years. But the universe invites reflection, not haste. It invites observers to imagine themselves as part of a cosmic lineage, stretching backward beyond memory, stretching forward beyond imagination. If universes arise from one another, then humans made of atoms forged in dying stars, shaped by galaxies, shaped by ancient collisions, are part of an unbroken chain stretching into eternity. This is the emotional weight of cosmic ancestry. It dissolves the illusion of isolation. Humanity is no longer alone in time. It stands in a universe that is itself a descendant, a universe shaped by echoes of a previous existence, a universe that will one day seed the next. There is comfort in this idea, but also awe because it suggests that endings, however final they appear, never close the book completely. They simply turn the page. If galaxies can die and yet give rise to new galaxies, stars can explode and yet plant the seeds of life across space, then why should the universe itself be exempt from such a pattern? Every collapse may be a seed. Every end may be a doorway. In this way, cosmic death becomes cosmic renewal. The universe breathes in and out across eons, each expansion marking a new beginning, each contraction or dissolution providing the raw material for what follows. And if this cycle has occurred not once, but countless times, then humanity stands upon the latest crest of an eternal wave, one that has been rising and falling since before time began. This is the deepest reflection of all. The universe humans inhabit may not be the first, nor the last, nor even one of the early ones. It could be part of an infinite heritage of universes, each remembering the last, each preparing the next. The cosmos becomes a tapestry woven from cycles of creation and dissolution, patterned with echoes, embroidered with shadows of former worlds. And within that tapestry, humanity is a brief but luminous thread. In this final reflection, the universe appears not as a cold mechanism, but as a story. A story told across unimaginable distances and unimaginable ages. A story of renewal, inheritance, and transformation. A story whose chapters stretch across the deaths and rebirths of universes themselves. It is a story that does not end. If this cycle is real, then somewhere in the deep future, long after stars fade, long after galaxies unravel, long after everything familiar disappears, the universe will again drift into a state where mass dissolves. Time loses meaning and geometry transforms. And in that silent moment, When the current universe takes its final breath, something extraordinary will happen. It will become the beginning of another. The echoes of this universe, its black holes, its structure, its final Hawking radiation, will imprint subtle patterns into the newborn cosmos. Those patterns may one day be discovered by distant minds, living billions of years in the future, wondering as humans do now, did something exist before our universe? And they too will look into their cosmic background. They too will find faint circles. They too will sense alignment. They too will suspect continuity. The cycle will continue. This is the profound beauty of cosmic ancestry. It transforms the universe from a single miracle into an eternal lineage of miracles. And in the light of that possibility, the human question, how did the universe begin, shifts into something larger. How many times has the universe begun before? And how many times will it begin again? The universe does not answer. It only leaves echoes. Echoes for curious minds to hear. Echoes for future universes to inherit. Echoes that whisper, softly but endlessly, the end is never the end.